All right, today we're going to take a look at function notation. So we're first going to start with what a relation is. A relation is a mapping or relationship between two quantities. And think of that as an input and an output. All right, now we're going to take that a step further and look at a further classification of a relation, which is a function. So a function is a special type of relationship, where each input has exactly one output. So we've taken a look at functions before, especially in that first unit. And our next thing is think of a soda machine. So I want you to recall that time when we went as a class, we went to the soda machine, and we watched how the soda machine works. You put in $1, you get out one soda. So for that particular soda machine, our input is the button you push. So that's what you put in. And the output is the soda you get. So your input, you put in, or you push a button, and your output, you get that soda. So whichever soda you choose. All right, now we're going to think about and what we talked about. If I hit a button and I get more than one soda, then the machine is not functioning. Now it's awesome, you get an extra soda, but it's not functioning, and we talked about that. It's not a functioning soda machine. But there may be more than one button that gives the same type of soda. For example, if you take a look at any of the soda machines, you may have two selections for regular Coke. So typically you'll see at the top two buttons might be for regular Coke. That's okay. And that's okay since each button has its own unique soda. And another example, think about it with the soda machine. If you hit saying I want regular Coke and you get Diet Coke, you're getting a different output, so it's not working there. So each input, each button you push, you're going to get one soda out of it. So we're going to take a look at a few different equations that are functions. So an example of an equation that is a function would be y equals x, which we've taken a look at. That's a linear line. Another example would be y equals 1 over x. Another example would be y equals 4. And then we can have long extensive equations such as y equals x cubed minus 4x squared plus 6x. So those are all functions. Now examples of equations that aren't functions are y equals plus or minus x, because that input, you're going to have some different outputs there. And just as a heads up, most equations we're going to look at this year are functions. And I'll be clear to make sure which ones aren't functions and which ones are. All right, now we do have the next one we're going to take a look at as mapping. So mapping, typically you'll see them as two ovals. The first one will typically be your input. The second one will be your output. You'll also see that as x and y is independent, dependent, so those are a few different things. So an example of an input or mapping function that is true, that is a function. So let's say we have the input 1, -3, 5, and the output 0 and 2. Now 1 can go to 0 and -3 can go to -2. Now 5 can also go to 2, and that's still a function because each input, each our values 1, -3, and 5 only have one output, 0 or 2. Examples of input-output functions that are not functions, for example, would be if we had the input, same thing, 1, -3, 5, output 0, 2. And if 1 still went to 0, 3 went to 2, but that -5 went to 0 and 2, that input 5 has two outputs. And for a function, it has to have exactly one output, so that's not a function. All right, now another example that you will see is a table. So with the table, sort of the same type of setup as input-output, except instead of ovals, we're going to have a table. So we have input-output, and this one we won't have arrows with it. We will have lines though. So let's say we have 1, -3, 5, and then the same output. So 1 to 0, -3 to 2, and 5 to 2. That works because each of our inputs have only one output. But an example of a table that is not a function, once again we have our input-output, would be similar to the mapping above. So if we have the inputs 1, -3, 5, and 5, so 1 goes to 0, -3 is 2, 5 is 0, and 2. So the 5 gives, that 5, or the input of 5 gives 2 outputs, so we don't have a function there. Alright, I moved it down just so we could take a look at the ordered pairs. So ordered pairs, we're going to take a look at those as a set. So an example of a function as an ordered pair, based off that, would be 1, 0, 3, -2, and then 5, -2. Actually, we've been using 2, so let's just stick with that same value. I was referring to my notes. All right, so we have ordered, or this is an example of ordered pairs as a function. Example of ordered pairs not in a function would be 1, 0, then we have 3, 2. So far it's a function, but then we get to the input 5 and has an output 2, and then that input 5 also has an output of 0 as well. We don't have a function because that input of 5, once again, has 2 different outputs. Example of it as a graph, and once again just referring to the same type of thing that we looked at these examples. So we would have 1, 0, 3, 2, and then 5, 2. So this is a function because it passes, and I know y'all took a look at this last year. Okay, I'm going to type this. But it passes the vertical line test. So if we map to the other one, or graph the other one, we do have 1, 0, 3, 2, 5, 2, and 5, 0. This would fail the vertical line test because once we did a vertical line, so think of a vertical line, and we moved it to the right, it's going to hit 2 points at one time. And to pass the vertical line test, we have vertical lines, so straight up and down. And as we move across the graph, it only is going to hit one dot, one ordered pair at each time. So since it fails the vertical line test, and this is looking a little odd, it is not a function. All right, now we're going to take a look at function notation. So first thing in that first blank, we're going to put f, and then in parentheses we'll put x, and then it's going to equal y. Now that first part, that x value, that's our input. That's going to be our independent variable, and it's inside the parentheses. So it's input, independent variable, inside the parentheses. Our y values are output. That's our dependent variable. So it's outside the parentheses. All right, so we're going to use the equation y equals 4x minus 5 with the x value of 2, just to take a look at the representation of that equation in different ways with function notation. So the first thing we have a look is that specific x value is 2. So when we have function notation, we're going to read this as f of 2 equals 3. So when we were to solve that equation, we substitute 2 in for x, we would get a y value of 3. So we'll read that as f of 2 equals 3. And just the work behind that, so we have f of 2, and that equals 4 times 2, since we're substituting 2 in for x. And so we'll get f of 2 equals 8 minus 5. So f of 2 equals 3. So that's our equation, our formula for that. In general, that would look as f of x equals 4x minus 5. You can look at f of x as a really fancy way of saying y instead, and it emphasizes that input and output variable that we're looking at. So in English, we would say when the input is 2, the function f makes an output of 3. Let's move that up and italicize. Oop, that did not italicize it. There we go. All right, so in general, we would say for an input x, the function f makes an output of 4x minus 5, or f multiplies the input by 4 and subtracts 5. So we're going to take a look at next how it looks in math. All right, let's take a look at what a function, this particular function, looks like in mapping. So we still have our input-output, and since we have the input 2 and we have the output 3, 2 will go in the box or an oval, and we'll draw an arrow to 3. Now in general, we have our input of x, and that will go into the output of our function, which is 4x minus 5. So that's what we're looking at with that input-output. Alright, so let's take a look at this with variables. So with variables, when x equals 2, y equals 3. And in general, we just have our equation. Y equals 4x minus 5. So on a table, we would have our variable when x is 2, we get a y value 3. Now in general, we have infinitely many rows, infinitely many columns, since that function indicated by those arrows goes on to infinity and beyond. So we can't really say that in general. It has to be specific to certain values, and it looks really odd. All right, as an ordered pair, we have 2, comma, 3. And in general, that ordered pairs, once again, we have infinitely many ordered pairs because that function has infinitely many solutions. And on a graph, we have 2, 3, and in general, that graph will be just the graph of that particular function. So I know this is sort of rough, but this is a little hard to do on this particular pen right now for some reason. All right, but I hope you'll have a great evening, and we'll be taking a look at more at functions, evaluating, and all that fun stuff tomorrow.